So we mentioned we mentioned transverse waves before, where we said that the where's the let me just get a pen. So we said that the oscillation was up and down in this case, but the propagation was to the right, and they were at right angles to each other, and so we call that, and the name of that type of wave is a transverse wave. So what we'll look at now is the other type of wave, which is called a longitudinal wave. So this is a longitudinal wave, and in the same way as the transverse wave in the same simulation, we've just highlighted a couple of these particles, and they're just moving only back and forth. So they're oscillating. In fact, they're all oscillating, but the highlighted ones are easier to see. So they're all oscillating forwards and backwards, but the propagation is generally moving towards the right. So we can see that these directions this time are parallel to each other. So in longitudinal wave, it's written there, the as it says that this particle displacement, or we could also say that oscillation is parallel to the wave propagation, the phrase I mentioned earlier on. And I did mention briefly that water waves are not transverse. Now, they are according to your GCSE specification, I believe, but technically they're not really transverse. So this is a transverse wave here. Everything's moving up and down, but the energy, the information, the pattern is moving from left to right. This is actually a water wave. And they don't move up and down or left and right, they move in circles. If you think about it, that kind of makes sense, because we know that when we are at the beach, water comes towards us and then goes away from us. So it's not, we also know that water goes up and down because we see it on the water. So in actual fact, water waves are not technically transverse waves, but they do get treated like transverse waves in your GCSE specification. Then there are these ones, Rayleigh surface waves, which are similar to water waves, but you don't need to know anything about that. So you only need to know about these two. But yeah, they're longitudinal and transverse waves. So with the longitudinal waves, measuring amplitude is quite tricky, because we can't take a ruler like we did before, like here. We can't measure the height of it, but there will be a more noticeable actual wave. So if we go to this simulation, waves intro, I think it's called, waves intro, and we look at sound. I might just mute that for a moment. First of all, what is a sound wave? A sound wave is just produced by vibrations. So this speaker makes these it just vibrates back and forth. It's already slowed down now. It's really slowed down. And if we were to, this doesn't show it as well as my previous simulation, but we can see the particles are jiggling back and forth. And if we go back to the waves here, this is maybe a better way to see it, really. So if I show a high amplitude, we can just see a very clear difference between where the crest is and the trough is. So it's very dark. There's a very strong difference between the two. Whereas if I have a low amplitude, there's not much of a difference. So they're just kind of like both sort of like light and slightly less light grey, right? So that's, and how could I actually make that look like a wave? What I can do is I can measure the pressure at different points. So if I measure the pressure there, we'll see that over time the pressure is going up and down. When the air particles are pushed together, then it's going to be high pressure, and when they're stretched apart, it's going to be low pressure. So looking back over here, we can see sometimes they're squashed together, sometimes they're stretched apart. The place at which they are squashed together, we call that place, which moves around, we call that place a compression, and where they're stretched apart, we call it a rarefaction. Now, there's another word in waves topic called refraction. That's not the same word, but it does look annoyingly very similar. Rarefaction is where the particles are stretched out, spread apart, lower pressure point, and then when we look at like light changing direction as it goes through water or glass, that's called refraction. Very similar looking word, but what we're talking about here is rarefaction, so not refraction. Anyway, back to this one here. So we can measure the change in the air pressure over time. And if I were to increase the amplitude, then what we're going to see is a more noticeable change in the air pressure. Okay, so the difference between high pressure and low pressure is much greater if the amplitude is higher. With a sound wave, when the amplitude is higher, how is the sound different? How does it get experienced differently? It sounds louder. And how does it sound differently if it's a different frequency? A high frequency is a high pitch. So I can demonstrate that, I think, with if I show my sound. Hang on. Oh, okay, I need to pause it up here. Right, so I've just turned the sound on here. I'm going to turn the amplitude down a little bit. And I'm going to click play tone. So this is when the amplitude, the frequency is like midway through, and the amplitude is midway through. We hear this sound. Okay, hang on. We don't hear anything. Let's press play. Okay, hang on a sec. One more time. There we go. And if I frequency, it goes more high pitch. If I frequency, it goes low pitch. If I decrease the amplitude, it gets quieter. Now, annoyingly, this simulation has this other sound effect, which basically is just is showing the back and forth of the speaker, but that just leads to some confusion. The point is high frequency, high pitch, high amplitude, loud, and the opposite way around too. So okay, so I'm just going to I think I'll just stop the video there. That pretty much covers that. Oh, up here.